The purpose of this video is to introduce a whole family of different Fourier transforms. If you work in signal processing at all, or start reading the literature, you see just this whole alphabet soup of terms. So you see FT, FS, DT, FT, DFT, FFT, DCT, MDCT. You just get a whole bunch of these acronyms. And it turns out that these are all names of different types of Fourier analysis techniques. So the FT stands, for example, for Fourier transform, a term with which you should become familiar. In fact, all of the F's here stand for Fourier. The S in this case is series. The DT in this case is discrete time Fourier transform. This is a discrete Fourier transform. And you may ask yourself, well, what's the difference between a discrete time Fourier transform and a discrete Fourier transform? Well, we'll explain that in just a minute. FFT is a particular way of implementing a discrete Fourier transform. A DCT and an MDCT are mathematically related to these transforms. So there's just a whole lot of transforms here. So the purpose of this video is to try to give you an overview of which transforms are which, how you would know which transform you would want to use in a particular situation, and give you just a really rough idea of the sorts of, sort of a conceptual idea of the sorts of things that you might look for. So let's make all this alphabet soup go away, and let's build a table. In fact, the purpose of this video is pretty much to build the following table. I will have a time, a couple of columns that relate to time, and I'll have a couple of columns that relate to frequency. Okay, and it turns out that by looking at characteristics of a time signal and corresponding the characteristics of a time signal will tell me the corresponding characteristics of the frequency version of that signal, or the transformed version of the signal. And so for each signal, I'm going to look at, is it continuous or discrete time? And is it periodic or aperiodic? So that's what these abbreviations mean. And I'm also going to look at whether it's continuous or discrete in the frequency domain, and whether it's periodic or aperiodic in the frequency domain. And it turns out that different combinations of continuous or discrete time signals that are periodic or aperiodic lead to different combinations of either continuous frequency or discrete frequency and periodic or aperiodic transforms. So the one that you typically see either first or second is the Fourier transform. And this is something that applies to a continuous time signal that is aperiodic. And it turns out that the Fourier transform of a continuous time signal that is aperiodic results in something that's continuous in frequency and also aperiodic. So if I draw what this might look like, if I have a time signal here, suppose it's a rectangular pulse. This is actually used often enough that you see it quite a bit. In the time domain, I have a rectangular pulse that looks like this. In the frequency domain, I have what's called a sync function that looks something like this. This is actually drawn badly, but this is a frequency domain function. And you'll see it drawn either as P of F or sometimes the frequency domain variable will be omega. And if you have to convert between the two, omega is equal to 2 pi times f. Now, you should also be aware that the Fourier transform, this guy here, is typically a complex function. So for every value of f, it gives you a complex number. In this particular case, that's actually not an issue for reasons that will be discussed in another video. This actually, the Fourier transform of this rectangular pulse is only real valued. There is no complex value. But for the sake of trying to make things make sense, I'm not going to worry right now about the fact that the Fourier transform has complex values that are both real and imaginary. Okay, so the goal here is just to get sort of a conceptual understanding. So if we go back to our table, the next thing that we'll look at is a Fourier series. And the Fourier series is obtained when you have a signal that's continuous in time, but it's periodic. And since it's periodic, what ends up happening is that the frequency ends up being discrete, and it turns out that it's aperiodic. Okay, so if we go to our picture again of waveforms, if I have a periodic waveform, it might look something like this. So basically, in this case, I might have these pulses, and they started at minus infinity, and they're going out to infinity. And the Fourier transform, in this case, is actually going to be what we call a Fourier series. I'll have a value that occurs at a frequency of 0. I'll have a value that occurs at a frequency that is the fundamental frequency of this time waveform. So in this case, I guess this would be t0. This value will occur at 1 times, or 2 pi over t0. I have other values out here. The idea is that I only get values at integer multiples of this fundamental frequency. And I also have negative values out here. So this is the sort of thing that you see with a Fourier series. You start off with a continuous time, periodic signal, and you get a frequency domain representation that is discrete in frequency and basically goes on out to infinity and minus infinity. Okay, so let's go back to our table. And the next one we'll look at is what's called the discrete time Fourier transform. And the idea here is that we're going to have a signal that's discrete in time, hence the discrete time part of the Fourier transform. And this is going to be aperiodic. Okay, it turns out that because it is aperiodic, the frequency domain representation of it is continuous. Because it is discrete time, the frequency domain representation of it is periodic. Okay, so if we go back to our pictures here, if I have a signal that in the time domain is discrete, but not periodic, so I'm doing my best here to draw a signal that's not periodic, then in the frequency domain, the transformed version of this signal is going to be continuous in frequency, whatever that looks like, but it will be periodic. So if I have drawn this correctly, you'll look at this and say, except for that last nasty bit, that this, in the frequency domain, you get the same shape repeated over and over and over. Okay, well, there's one last combination, and this is what gives us the discrete Fourier transform. If my time signal is discrete and periodic, then my frequency representation of this signal is also discrete and periodic. Okay, and this is why it's called the discrete Fourier transform, as both the time and the frequency domain versions of the signal are discrete. So if I go back to my picture, we'll nuke these guys. And I have then a signal that is discrete and periodic. So this is meant to represent a signal that goes high for 3 samples and then goes to 0 for 3 samples. And it repeats this forever. Then in the frequency domain, I will have a signal that is also discrete and periodic and goes on forever. Okay, so hopefully this has been useful. We'll go back to the table just to summarize. So you'll notice, again in summary, if a signal in the time domain is continuous and aperiodic, then in the frequency domain its representation is continuous and aperiodic. A signal that is discrete and periodic is discrete and periodic in both domains. You'll notice that everywhere I have an aperiodic time signal, that corresponds to a continuous frequency signal. Everywhere I have a periodic time signal, that corresponds to a discrete frequency signal. So you can see that aperiodicity implies continuous and so on. You'll also notice everywhere I have an aperiodic frequency domain signal, I have a continuous time signal. Okay, so continuous time leads to aperiodic frequency. Every time I have a periodic frequency, I've got a discrete signal. So you can see there's a lot of symmetry here. And in fact, one of the things that you end up doing a lot in Fourier analysis is using all of these different symmetries. It turns out there's a whole bunch of symmetries for each of these different transforms. So with that, we will end this video.